show that they can get fairly large accuracy. At 1, it's about 80%, and if you take the top 3 candidates for entity and intent, you can get up to nearly 90+%. For movies and games and books and songs. So I said they deal with the commerce regime. And they also reported high probability words for each type. What do you want to do with things of every type? If the type is movie, then you might want to get photos or soundtrack or pictures or wallpaper or cast. If your target type is a game, then you might want cheats or downloads or play online. If it's a book, you want a summary or reviews or synopsis. If it's a music, you want lyrics or video or something. So if you have this precompiled structure of what you want to do with each type of thing, and you mention an entity with some context, it becomes much easier to understand what your query is about. But that's the first kind of queries, where you're actually mentioning an entity directly in the query. Perhaps an even more challenging set of queries is where the category is implicit in the query, and you're looking for the entity. You don't know what the entity is. And there's no reliable syntax clue for the search engine. The word order is relatively free because sending a telegram to the search engine at great cost. Capitalization is not there, or it's very rare. No one types capital N for new and capital Y for York anymore. The search engine is supposed to know that. There are no coded phrases. People don't quote New York anymore because, again, the search engine is supposed to divine what you have in mind. And there are very few functional or relational words. So verbs are pretty rare in query, web queries. So here are actual queries. So someone says, Hermitage Museum Bank River. And remember, the input to the search engine is not color coded. So what's the user looking for? Is the user looking for a museum, a bank, or a river? How do you know it? So it turns out that the information need here was most likely to be on the bank of which river is the Heritage Museum located. It's another typical query, Dolly Clone Institute. The user is looking for the institute where Dolly the sheep was cloned. How do you know that institute is the target type? How do you know that river is the target? Or losing team baseball World Series 1990. So I'm looking for a baseball team. I'm not looking for World Series, for example. Or Woodrow Wilson was the president of which university? You're not looking for a president, you're looking for a university. So we call this target type entity seeking queries. The previous one was, you might call it entity embedding action or intent queries. So we are starting to evolve this kind of catalog of query types which are entity oriented. And here is the second type of such queries, which has a target type in it, which may be implicit. And then they seek entities of that type. So there's some related work which tries to first interpret the query, and then in a second phase, probe a knowledge base with an interpreted query to give you entity answers. But we show here that that's not the way to go. The corpus and its statistics gives you really valuable feedback into how to interpret the query. In fact, multiple interpretations are simultaneously possible, and we need to score them together to come up with the entity answers. And I'll develop the story in a generative model because that's much easier to understand, and then we'll go over to a discriminative algorithm for ranking entities today. Yes?
Sir, it was like way back, like 6 or 7 years ago, I read somewhere that if we type in apple minus fruit in the search engine bar, then it wouldn't show us results for apple, which is a fruit. It would show the results that would apple anything else. But now that is not functioning. Why would the algorithms remove these kind of things? Because like in these slides, in this one and the previous one, we have studied how the search engine would go about it.
Right, so this is a little bit of a tangent, but let me answer that anyway. So very often, what features the search engine exposes to the interface or not depends entirely on complexity issues. So in the very early days of Alta Vista, you could actually suffix a query token with a star. So you could say, find me all pages which have some tokens starting with, let's say UNI star. So you get universe, university, universal, every word starting with uni. Okay? And that was a great feature in the days where the web had 500,000 pages. But, I don't know how much you know of the boiler rooms of search engines where, you have to churn through 12 billion pages, store them in not one, but probably 3 or 4 tiered indices, and then your query comes in, the query is immediately, it's almost like a Formula One pit stop team, descending on your query and fixing it up, right? It's like the query lands up, and within like maybe at most, let's say 50 microseconds, they have to decide if your query is geosensitive, is it time sensitive, does it have commercial intent, what region are you coming from, all kinds of things. What's the main topics of it? Is it a bad news query? So why do you need bad news queries? So you're researching about Hurricane Katrina or something, and then devastates New Orleans or something, right? And then you get this ad saying cheap tickets to New Orleans. That's an ad you don't want to give, right? There's this famous story from Andre Broder about a gruesome story of someone hiding a body in a suitcase and a Samsonite ad on the same page. You don't want that, right? So how to decide on commercial intent and bad news, and how to narrow down your ad options. If you're looking for geosensitive queries, then how to get your current coordinates and use that to read and web pages depending on the presumed location of the web source that they're ranking. So there's a lot to do. And then how does Google get by responding to your queries in under 100 milliseconds? You basically never touch this. Your query is then dispatched to about 300 servers. And then based on what they initially report, the decision is taken over whether to go to the tier 2 index or not. So it's a lot of work. And anything in the query which increases query complexity should be discouraged, right? So minus turns out to be a difficult operator because it just fetches a bunch of things and throws them away, right? So that's why those things are eliminated. Besides, apple minus fruit is not guaranteed to give you, if a document is talking about orchards and farming and what kind of pesticides not to use, you might even find fruit there. It's obvious from context that you're talking about fruits, right? So it's neither foolproof and it takes a lot of time. That's why they move it up. Yeah. Question? Yes? Do you have a question? All right. So just to repeat, our view of the annotated web is that we have a bunch of types under the subtype of relationship, and then types have entities like Major League Baseball teams has this particular baseball club called San Diego Padres, and then those are mentioned in web documents like by comparison the Padres have been to 2 World Series losing in 1984 and 1990. That's an annotated document. So now, so here's the challenge. Suppose I see this incoming query, which is not color-coded, losing team baseball World Series 1998. The problem is that pretty much any subset of words there will match something or the other in a type catalog. If I have a large type catalog, pretty much anything. So if I mistakenly think that World Series is the target type of the user, that the user is interested in some instance of some World Series, it's perfectly easy to match it to World Series hockey. The loss of match of hockey is not necessarily any worse than the loss of match of baseball. But that's the wrong type. Once I walk away from the right zone of the knowledge graph into hockey teams, I get it all wrong. And the only way to know that this is a bad match is that Padres, my correct answer, has very little correlation with hockey teams. They're not about hockey. So that information never comes from the query side alone, it also comes from the corpus. It's vital to exploit the corpus. So on the other hand, if I zoned in on the right region, on the correct region of the type catalog, namely Major League Baseball teams, so I'd match that. And in fact, there's now an inversion in order, so it may be a worse match than World Series, probably locally. However, this correct type of Major League Baseball teams has an instance of San Diego Padres, which appears in not one, but thousands or tens of thousands of web pages which discuss the Padres' loss in 1998. And those green words circle back to the query. That's the significant cyclic structure. your query hints at types which have instances which are mentioned on pages which have other query queues. So this is just one example of why regarding the query as a flat object is all wrong. Different tokens in the query have very different purposes. This is the very first example of just two purposes. Type hint, matchers or selectors in the corpus. And yet, this is a very non-trivial inference cycle which doesn't go just between the query and the corpus. It actually goes through the catalog into the corpus and comes back again. And your score for a particular entity is a function of this entire edifice. It's not a function of one document in your query. It's a function of lots of documents, the catalog and the query, where the query has been magically split into the right two parts. So in short, we need to discover query word roles. In this simple example, the red role and the green role. So speaking of language models for retrieval, let's follow that through into a more souped up model for this business. So the user starts with a secret answer, which is San Diego Padres. The user samples a type. So San Diego Padres is an organization. It's a sports organization. It's a major league, it's a baseball team. It's a major league baseball team. It's a major league baseball team in the US. When people ask for San Diego Padres, they don't ask for it as organization. They most often ask for it as a baseball team. So somewhere this type is being described as language through a sampling model P. And so the type hint words are baseball and team. On the other side, San Diego Padres is mentioned in a huge bunch of web pages. Use another sampling model with theta as parameters to extract words from them. And let's say in this particular context, you sample Lost, 1998 and World Series. And then you blend these two sides to form your query. When you blend, the colors are lost. You don't know if the word came down the left side or the right side. And the search engine has to split that up into the two columns. So more formally, here's a plate diagram. In the beginning, every type is hinted in a query using a language model P. So this beta is a hyperparameter, so just forget about it. So those are parameters P. For each query, there are Q queries in all. I have a secret, I have a set of candidate entities for this query. That's EQ. Each entity is described with a context language model having parameters theta. So P is the space of types. Each type is described with a language model with parameters P. For every query, there is a space of candidate entities. Each entity has a description language model theta. There is the secret entity which is the answer, E. Suppose the query is which physicist or which scientist played the violin, and my secret entity is Albert Einstein. Now, if I ask for Albert Einstein in a query, I ask for him by a type. I usually don't want to know about Einstein by the type biped mammal, but I don't usually say which biped mammal discovered relativity. I usually say which scientist discovered it. So that prior is enforced by gamma. And so I choose a secret type gamma. And then for each query word, so query Q has mod Q query words, I need to choose a corpus. So the corpus of the query is decided by this hidden variable called Z, which is a switch. Does this particular word hint at a type or does it match? Which scientist played the violin? Scientist is a type specifier. Violin is a context word specifier. So depending on whether Z comes up to be type or selector, I finally generate the word, which is the only thing I see finally in the query. There are all these hidden variables which I don't see. The only thing I see is the word, which may either be trying to describe a type using those two, or it is trying to describe the context of an entity. So this is the plate diagram in all its glory. In expression, it looks much easier. the probability of an entity given a query is the prior of the entity. Since I don't know what type the user had in mind, or what selector, the switch the user had in mind, what's the spread of the query, I iterate through all possible red-green splits. For a short query, that's not too bad. And for long queries, you can have different pruning schemes. I choose the type of the entity, I choose the switches, then I generate the type hint words given the type, and I generate the matchers given the entity. So I'm running out of time, but this generative story can be fleshed out into a discriminative model, like a support vector machine, where I want to score the positive entities over many negative entities. And the only interesting thing to note here is that I need to define a feature between the entity and the query, but I need to stick in the type and the switch variables because I don't know what that is. And I want to existentially and universally quantify for this. I want to say that the winning entity wins under its correct interpretation of T and Z compared to any interpretation of any wrong. So it's existential on one side and universal on the other side. The correct entity under its best query interpretation should win compared to an incorrect entity under any interpretation. So that leads to constants. This looks like basically for every query and for every good entity and every bad entity, the best interpretation of the good entity should beat the best interpretation of any bad entity. So this side is easy to do, but the max on this side with the greater than equal to results in non-convexity. So we give an interesting annealing protocol to do this, and this has connections to later work that's been published on support vector machines with latent variables. So I can talk about that offline to you if you want. And then the annealing protocol has an entropy term which you need to pull down to 0. And so it turns out that it's an authentic optimization where each authentic step is convex, but the overall program is not. So our test bed had about 200,000 types and about 2 million entries. And for annotated corpus, we had about 500 million pages with about 16 annotations per page. And we had about 700 entry search queries from Trek and INEX. The only reason we took Trek and INEX queries in this work was so that we had ground truth entities for each of them. They were converted to telegraphic form by humans, who also separately tallied their most probable type and answer entities. But they're not used directly in training the system. So this is reasonably practical. Our query answering system is about 3 times slower than one query. I'll not have time to go through all our experiments, but the main thing we wanted to study is there are these 2 extreme kinds of queries. One is where a human specifies the target type explicitly. That's the best you can get. It may not be always perfect, but it's the best you can get. The other is where the query engine is uninformed by any type constraint. So the whole user query is taken uninterpreted as a string, which is what previous generations of search engines used to do. And that's the genetic. The genetic is where no type is inferred, and human is some kind of an informal upper bound where the type is specified by a human. And we plot entity level. So you've already heard about NDCG, normalized discounted cumulative gain, and mean average precision and mean reciprocal rank. They follow the same trend, so we'll only show some of them. So the big suspense was, here is entity rank and here is entity NDCG. And here is the uninformed generic query system, and there is human type, human specified type. Where do our algorithms fit between the two? So it turns out that generative makes up for about 28% of the gap to human annotated queries. And the discriminative approach using SVMs with latent variables bridges about 43% of the gap between generic and perfect, or not perfect, but human. So discriminative is significantly better than generative, and that's not a new story, that's always been the case. And it's not like we always win. There are queries where we lose compared to generic as well, but there are many more queries where we gain. So I'll skip this experiment. Just summarize part 2 as I have only 2 minutes left. So a large percentage of web queries contain a mention of a target type as well as entity level. And the identification of the target type hint is rewarding, but it's non-trivial because the query is so short and pretty much everything matches something in your catalog. And joint query interpretation and ranking approach is significantly better than a two-stage approach. It also improves type inference, which is the second experiment that we showed. And again, the dataset is publicly available at this URL. All our 700 queries with their interpretations and the snippets. So in conclusion, the catalog is the way humans are trying to structure unstructured knowledge in the web. That's the knowledge base. But the catalog is always incomplete. It's always evolving. And to answer many interesting kinds of queries, it's not enough to depend on the catalog or knowledge base alone. We have to connect it to the unstructured corpus and answer queries collectively. And one way to look at it is that everything is a corpus. Even the knowledge base is the corpus. It just lives in the web corpus. So Fernando Pereira, who is head of Google Research, has a funny way of saying it, which is the knowledge base is part of the corpus. It just has some funny brackets in it, that's all. And these annotations which pass between the catalog and the corpus, they establish these valuable information pathways beyond what's useful in the knowledge base alone. And if we have those valuable pathways, those red links between the catalog and the corpus, we can support many powerful queries going beyond what the catalog itself has. And we are focusing on semantic interpretation of telegraphic web queries, as against well-formed questions like in the Watson search engine of IBM Research or Wolfram Alpha, who can do very well if your query is very well formed and you can get a precise linguistic lock on what the query means. But they are very brittle in the sense that it's very easy to fall off the edge of what Wolfram Alpha or Watson can handle. And if you walk out of that, you immediately jump into this soup of completely unstructured knowledge. And what we're trying to do is to answer some of those middle ground and pushing our luck with the tail queries, so that as we drop off what's explicitly in the knowledge base, we don't degenerate immediately into unstructured web search. There's something in the middle where we can do a lot with these partial linkages between the knowledge base and the web. So that's the talk. There's some additional reading in here that you can look at. Thank you for your attention. Happy to take any questions.
Any question?
Like people from lunch, so thanks.
I have a question.
Yeah.
Thanks for your interesting talk and nice experiments which you all have conducted. So my question is rather a little basic. So you talked about the telegraphic queries, and I recall you mentioning at one point in your presentation that telegraphic queries kind of make it harder to to process the search and to give the results finally. So, but at the same time, you see from a user's perspective, sometimes let's say a student wants to kind of he wants to find a Java sample code to get a client server application, for example. So let's say case one, he types in the search query how to write Java code to develop a client server application versus Java client server code. So it appears as if this case 2 gives better results as of now.
Other one. So some results, and if you want to push them out of the equilibrium, then at least one party has to take a different step. So there are papers which deal with verbose queries in the information retrieval literature. So how do you subset a query? If your query is too long and you're scared that firing it up over your current ranking function will actually damage your case, then how do you prune the query ahead of time? That's a very interesting topic. So I gave a tutorial about that at the last web conference. So one of the links there describes that sort of work, how to deal with verbose queries. But it's not just a matter of surviving verbose queries. You thrive on verbose queries. And so some of the work I'm describing is relatively tolerant to verbose queries. Start identifying entities and relationships between them. So one thing I haven't touched upon at all is relations. I just talked about entities and their types. And that's one kind of relationship. It's probably the most important kind of relationship, but also arbitrarily named relations between entities. And that's starting to get mainstream attention. But yeah.
Hello sir, I'm very happy to meet you finally. So, recently there was this experiment conducted by DuckDuckGo, it's a search engine where they connected this bubble experiment, in which they say that Google puts all the users into some sort of a bubble. and it gives inconsistent result. As in, if I type so a query, if I type, it's going to be different from my friend who's in US. It's going to be different. And keeping this in mind, with what we were talking, knowledge base, it can only be a part of a search engine. As in, the regular results have to be given, and with if the search engine is going to give any other clusters, it's only going to be a part. I mean, it's just going to answer the question at the top. What do you think actually will be the parameters that a search engine could take into consideration to finally give the final SERP in such great speed?
Well, there's no one answer, right? If I interpret the first part of what you're saying, there's always a tension between sort of predictability and personalization. It's making possible to understand who you are and to track your usage and lots of things. And many people are starting to get uncomfortable about the extent to which Google knows. They definitely know your current coordinates to within 100 meters, if not better, 50 meters. They have a fairly, if not Google, they're actually a startup which looks at your topics of interest or the time series in the past. And there are some overriding seasonal patterns. Wedding around Christmas, then maybe gifts and so on. That rises up, holiday travel and so on. But otherwise, they understand what topics you're interested in and what commercial intent that has to show ads and so on. So if you're doing that, you're browsing the web and I'm doing it, it should show very different things. That sometimes makes it difficult to report. I would say, oh, just Google this particular query and then what you need, and you may not find it because you're a different user. There's always a tension between that. There's another area of text search and ranking. I don't know if it was mentioned yesterday or it will be throughout this conference. Another big area of search ranking is diversification. So if you have different criteria for ranking and you want to reach some kind of Pareto optimality, what do you show in the finite real estate? So a simple example, if you say John Smith, there are so many John Smiths and you have this precious 10 slots, okay, 10 slots or 10 shots, and you want to hit some sizable user population with at least one of those shots. So, given the different John Smiths on the web and their respective prominence and your personal information, how do I choose 10 John Smiths to show? I don't want to show you 2 pages of the same John Smith. Right? I want to maximize the probability that you will be satisfied by at least one of the 10 links, hopefully within the first 3. So that's a very complicated organization. And think about it, the consideration there is, if I have seen one web page, is it still necessary for you to see another web page? See, there's this information retrieval clustering that if pages P1 and P2 are very similar to each other, then either both of them are relevant to your query or both of them are irrelevant to your query. And that's fine, but it's useless. Clustering is useless because, so what if P1 and P2 are similar? If my query is cubed and P1 and P2 are very similar, then show me exactly one of those, don't give me both. So the first page where 10 links play out is a very different game than scoring each page with regard to the query.
Sir, and the query itself is actually various types. I mean, it's not necessary that all the queries should be meant for the KP. How can it be actually found out? I mean, is it by a question mark or something like that? I mean,
there are many techniques, none of them foolproof. So, as I was saying, when your query gets into the system, there is a bunch of classifiers which immediately scan the query with various labels, like geosensitivity, temporal sensitivity, commercial intent. So one of them is whether this has anything to do with knowledge base, or is it safe to probe the knowledge base for this query. So there are various classification schemes. Typically trained using clicks. So if you ask the query, then you click through to Wikipedia or to a previous display, then it's an entity seeking query. So you train the system with things like that. So the other thing to remember is that any commercial search engine has 10 years of priceless click data. And that gives a huge input to the system.
Yeah, and, one last question is, with respect to the search user interface as such, I mean, why is that the traditional interface of 10 links is not being changed? Is it actually the highly preferred one? Will that
It's
be
again,
one?
whatever is normalized in dominant practice, but things are changing. I mean, so there's this, I used to work in the same corridor as the person who invented the IBM trackpoint cap. So he's a user interface guy, and he used to say that when researchers try to develop interfaces, that's usually a dangerous thing because somebody stopped and asked me, have you flown a helicopter? Neither have I. Very few people drive helicopters. So people who design interfaces should know that users don't fly helicopters. They don't like flying. So typically the simplest paradigms stick, right? There are so many ways to show graphs. And in fact, if you look at the stuff on your laptop's hard disk, is a tree the best way to display it? No, but the data tree has stuck because it's just so easy to manipulate. So similarly, if you think of an interaction or a marquee-down approach to querying, what has really stuck is the query suggestions and the pull-down, and you select among the queries. Right? And there are very nice papers on given past query logs and how far you have typed, how should you get possible completions or variations of the query, and what pass signal feeds into it in the sense of if people have selected certain queries before, how do you use that to guide future query expansions and suggestions? But that's one interface which has become possible. I'm pretty sure such suggestions from the knowledge base will come about.
Thank you.
Yeah.
So Google is also having some social network